Question 7 is a mixed air problem coupled with a heat transfer problem. It requires basic understanding of the air handling schematic provided and psychrometric charts to derive critical properties of the air. Finally, it requires knowledge of fundamental air mixing equations. Initial critical thought solution elements. 1. What are you solving for? The refrigeration load on the cooling coil used in an air handling system. 2. What is the fundamental process? Total heat transfer for air and adiabatic mixing of moist air streams. 3. What are the first considerations to find the solution in connection to the fundamental process? Organizing the various air streams and identifying variables for the necessary equations. 4. Are there key assumptions? Sea level altitude, standard air, adiabatic mixing, and steady flow energy transfer. You're solving for the load on the cooling coil as it transfers heat from an airstream. The coil connects the refrigeration system with the air handling system. In this question, there's the common circumstance of the coil's heat transfer being exactly equal to the air's heat transfer. The BTU per hour taken out of the air in order to cool it is the same BTU per hour taken in by the coil as it does the cooling. To solve for the heat transfer of one is to solve for the heat transfer of the other. The schematic given in the question is a basic air handling setup, with the small added variation of a bypass damper, which is also common. The question says the bypass doesn't operate during max load conditions, and you must solve for max load conditions, so the bypass damper can be ignored. There's nearly no heat transfer information for the coil. The little there is insignificant and can be ignored. Though you're asked to solve for the heat transfer load on the coil, you don't have any useful data to build up a heat transfer equation for it. You need things like GPM fluid flow and temperature differences for entering and exiting water. None are given, and none can be derived. What you do have is lots of data on the air, so the changes to the air will directly equal the refrigeration load on the coil, which is the thing causing change to the air. Looking at the information provided in the question and its accompanying schematic, it should be obvious that you have outside air mixing with return air, which is then cooled by the coil to become supply air. Notice you're given data for these air streams, such as dry bulb and wet bulb temperatures and relative humidity percentage, all of which are different. This means that the coil changing the air condition is engaged in total heat transfer. If it's not obvious why this is a total heat transfer circumstance, consider a process of elimination. You're solving for load, which by definition is a heat energy transfer rate. The relevant data you have to solve for the load is all for the air. The air is standard. The three standard air heat transfer equations, which you should have memorized, are total heat, a change in enthalpy, sensible heat, a change in dry bulb temperature only, and latent heat, a change in humidity ratio only. Just looking at the data provided for the air without solving anything, you can see changes in both the dry bulb and wet bulb temperatures. So sensible heat and latent heat transfer equations are eliminated. The change in enthalpy in the total heat transfer equation captures both the dry bulb temperature change and the humidity ratio change. With these circumstances understood, begin the calculation process by setting up the total heat transfer equation for the air as it passes through the cooling coil. This video is brought to you by ExOverZero, which offers the best PE study tools possible. To purchase our practice exams, use the link below. Energy flow in BTU per hour is equal to airflow in CFM times 4.5 times delta enthalpy. The energy flow is the load coming out of the air. This is exactly the refrigeration load you're solving for. The airflow must be what's coming out of the coil, which is 20,000 CFM of supply air. No air is added within the coil, and you have incomplete information about the air flowing into the coil. Notice there's 5,000 CFM of outside air that eventually comes into the coil, but before it comes in, it mixes with an unknown amount of return air. The 4.5 comes from the product of standard air density and a time conversion. The delta enthalpy is the difference between entering and exiting enthalpy. As the air is being cooled, it will lose enthalpy. So it's entering enthalpy minus exiting enthalpy. Use the psychrometric chart to determine these enthalpies. But first notice specifically what the entering and exiting enthalpies consist of. The entering air is the mixture of the outside air and the return air. So an air mixture calculation must be done to find entering enthalpy. Keep in mind that air mixture calculations require mass. The exiting air is a simple lookup from the information provided by the question. Now to the psychrometric work. Use the chart to find the enthalpies of the 3 airstreams and the volumes of the 2 mixing airstreams. You'll need the volumes of the 2 mixing airstreams to derive the masses. Masses are required for mixed air calculations. The outside air is 90 degrees Fahrenheit dry bulb, 74 degrees Fahrenheit wet bulb. Look up where the dry bulb temperature of 90 intersects with the wet bulb temperature of 74. Enthalpy is roughly 37.7. Volume is roughly 14.18. Return air is the room air. You should know that. It returns from the conditioned space. The return air is 80 degrees Fahrenheit dry bulb, 50% RH. Look up where the dry bulb temperature of 80 intersects with the relative humidity of 50%. Enthalpy is roughly 31.4. Volume is roughly 13.85. The exiting air is 58 degrees Fahrenheit dry bulb, 56 degrees Fahrenheit wet bulb. Look up where the dry bulb temperature of 58 intersects with the wet bulb temperature of 56. Enthalpy is roughly 23.8. This can be put into the total heat equation here. You're now only missing the enthalpy of the mixed air entering the coil. To find this, do a mixed air calculation for the entering airstreams. For this, refer to the NCEES Mechanical Reference Handbook, Section 9.2.3. Have the 3 equations given memorized. Use the first 2 equations to solve for mixed air enthalpy. The mass flow is calculated as volumetric flow in CFM times the reciprocal of the volume. Mass flow is in pounds per minute. Simple unit analysis and critical thought demonstrates this equation. Outside air, 5,000 times 1 over 14.18 is equal to 352.6. Return air, 20,000 CFM exiting air, minus 5,000 CFM outside air, times 1 over 13.85 is equal to 1,083. Use the second equation from Section 9.2.3 in the reference handbook to determine the mixed air mass flow. 352.6 plus 1,083 equals 1,435.6. Now set up the first equation from section 9.2.3 in the reference handbook to determine the mixed air enthalpy. 352.6 times 37.7 plus 1,083 times 31.4 is equal to 1,435.6 times mixed enthalpy. So the mixed enthalpy is 32.95. Put it in the total heat equation here and solve. Total heat transfer is 823,500 BTU per hour. You're asked for the load in tons of refrigeration. Have this conversion memorized. Divide by 12,000 and get 68.63 tons. Option C. To get good at questions like this, study ASHRAE Fundamentals Chapter 1, Section 10, subsection titled Adiabatic Mixing of Two Moist Airstreams. In the ExOverZero practice tests, do problems Test 1, number 6, Test 2, number 8, Test 3, number 6, Test 4, number 9.